Section 2.4 talks about the discovery of the electron, and before you think that this is kind of a dead field and that nothing's really new in this area, just this last year or so they made a new discovery about electrons. They did some experiments to see how round electrons are in terms of their negative electrostatic field, the negativity basically of the electron as it extends into space. And they found that this was actually perfectly round to the point where they could detect no asymmetry whatsoever. And they were using some pretty sensitive instruments to do this. If you want to get an idea of how sensitive the instruments were and exactly how crazy round an electron really is in terms of its perfect symmetry, then you could just picture this. If you took one electron and blew it up to the size of our entire solar system, there's no asymmetry, meaning there's no deviation from roundness that could be any thicker at that point than a human hair. And that's how incredibly perfectly round these things are. So it actually really was kind of a crimp to some of the theories of the universe and how the universe formed, because it is preventing for the detection of some other types of particles that they were hoping were there, but they haven't discovered yet. But in any case, the original information about electrons started with J.J. Thomson looking at the cathode ray tube, where you put some material inside on electrodes. Cathode and an anode just basically means you're holding a electrical potential between two metal plates, and you have a mostly evacuated tube in the center, meaning that there's not a whole lot of material inside the tube. You charge up a very high voltage, so a potential difference of very negative versus very positive on the two sides, and you see these rays that travel through this. Well, he didn't know what they were at the time, but those were actually electrons. And what we were seeing is that the rays traveled in this nice straight line from one side to the other, that it didn't really matter what the material was, what that metal was on the two sides of the cathode ray tube. You still got this same set of movement of this beam across that was later found to be electrons. And they found that the electric field of the objects, this ray that went through this cathode ray tube, was negative. You can do that just by exposing it to different electronic fields and seeing which way it bends. Well, now if we look at electrical charge and electrostatic forces, we have to kind of understand what positive and negative is really referring to. So an object can have an electrical charge. That electrical charge can be positive or negative. Okay? And what that positive or negative refers to is it refers to electrostatic forces. That's forces that either push away or attract an object from each other, two objects from each other. So if things have the same charge, meaning both negative or both positive, then they will be pushed apart from each other by electrostatic forces. If they have opposite charges, like one positive and one negative, they will find an attraction, so the force will be towards each other. Okay, so that's what we're talking about. And when we talk about an electrical field, because we're talking about how electrons have a negative electrical field that results in electrostatic forces, and we can say that the electrical charge of that field is negative in character. When we talk about this idea of electrical field, we're talking about the distance in space that you can feel that positivity or negativity of that electrical charge, the distance that that electrostatic force can operate against. J.J. Thomson also, in subsequent work with these cathode rays, looked at sending these sort of rays through a tube. And you could send it through, and you had electric and magnetic beams of different types. Electric and magnetic fields, so two different types of these fields that can influence the beam. And you can, with this, look at the deflection of the beam in different strengths of field. So you create the beam, and then you bend the beam through magnetic or electric fields. And when you see exactly where you can get the beam to go straight, and you measure the amount of field that takes, that can give you an indication of how much charge is on that particular object because of how much charge it required to get it to bend or to not bend in certain fields. Well, what this tells us, a certain amount of charge present on a gram of material. Basically, this is we know now of electrons, gram of electrons. That you look at this mass to charge ratio, and what we're looking at is something that is about 2,000 times smaller than a hydrogen atom. So that brought up a couple of issues at the time. They thought that atoms, such as hydrogen atoms, which is the smallest atom that we know about and that they knew about at the time as well, if something is smaller than that, then these things that we're measuring must be smaller than atoms, and therefore perhaps are part of atoms. A portion of it, as opposed to a full atom worth of material. Millikan performed an experiment subsequent to this to try and determine the actual charge on one electron, on one of these particles that were being shown in J.J. Thomson's experiments. So what we have is we have a positive plate that you can charge up to be more positive or less positive up here. We're spraying some stuff through. The positive plate has some attractiveness to things that are negatively charged. So when these little oil droplets go through and we blast them with some radiation, which we can talk radiation later, and interestingly enough, it's pointed right at this viewing microscope, which was probably not very good on the eyes, but whatever, it was a great experiment. But this radiation ionizes the particles as they fall through it, meaning that it strips some of them so that there are additional electrons on the droplets, and those additional electrons on the droplets are making these particles negative. So the theory of this was that if the electrons, or these particles that were being seen in these ray tubes, cathode ray tubes, were individual discrete particles, then each of them would have a set charge, and whatever the charge that the particle took on would have to be some number, some multiple of the charge of an individual negative electron. Okay, so this idea is if we have a charge of, say, 500, then that must have a certain number of electrons to it. And if it had half that number of electrons, the charge would be 250. And if it had a quarter of that number of electrons, it'd be etc. So the measurement was actually performed by charging the plate underneath it negatively, so that the negative charged oil droplets that were going towards that plate would be slowed down by a certain amount, depending on how much charge was on the individual oil droplets. And you could actually get them to go back the other way if you charge this plate up enough or just stay suspended. And by knowing exactly how strongly you charge that plate at the bottom, you could determine exactly how much charge was on an individual droplet. Well, all of this basically came out to the conclusion that whatever the charges on the different droplets were, it always had some multiple of this negative 1.60 times 10 to the negative 19th coulombs, and coulombs are a unit of charge. So that means if I had 1 electron worth, then that would be the charge. If I had 10, then I'd have negative 1.6 times 10 to the negative 18th coulombs of negativity on that particular oil droplet. But none of the droplets had fractional amounts of this. They all had some multiple of this 1.6 times 10 to the negative 19th coulombs worth of charge. Well, you can take that previous information about the mass to coulombs per gram amount, right? So negative 1.76 times 10 to the 8th coulombs per gram. So we have 1 gram for negative 1.76 coulombs, times 10 to the 8th coulombs, and each individual electron is negative 1.60 times 10 to the negative 19th coulombs. So if we multiply this out, coulombs will cancel, and we're left with grams for each one of those particles, and that's where we get the size of an electron. An individual electron, therefore, we've measured this mass, not by scale or anything like that, but just through proportionality and ratios, to be 9.10 times 10 to the negative 28th gram. Pretty small. So about electrons, here's the summary. They're negative, know that. Electrons are the same regardless of where we get them from, which is true. We have found no evidence yet in physics that this is not the case, that an electron is an electron is an electron. The electrons are much smaller than atoms. Okay? Historical side of this, J.J. Thomson discovered the electron with these cathode ray tubes, plus measured the mass to charge ratio of the electrons. And then Robert Millikan quantified the individual electron properties, such as finding out the charge per electron, which allowed him to find the mass per electron. Okay? And if you haven't seen this before, the nomenclature for electrons is a little e with a superscript of minus charge. This means electron.